This is the second lecture for Chapter 8, and we're going to start off looking at Lewis structures. Very exciting. I don't know how you guys remember these from last year, but they actually go pretty easily after you've done a few of them. Hopefully we have some good luck with it. So the idea here is to kind of try to figure out how these atoms are structured together when they all come together. And there's a couple rules that we'll go through when we're putting them together. So here's a nice easy way to start with. I'm going to mostly ignore the wording on here. You can pause it and take a look at that on your own. But when we're going through and you have just a formula that's given to us, so that's PCl3. What you should do is figure out how many valence electrons each of these guys has. So when I look at phosphorus, that has 5, and each of the chlorine is going to have 7. So if you do the math, you get what you have here at the bottom. So I have 26 electrons to deal with. The next thing is you should draw these things structured out so the least electronegative element is going to be the center, and it can't be hydrogen because it only has 2 electrons to work with. So phosphorus is the least electronegative, so I put that in the middle and surround it with the other elements, in this case chlorine. And then you put a bond between them. Each of these bonds represents 2 electrons. So I'm going to subtract that from my original total, which was 26, and now I'm down to 20 electrons. Moving on from there, simply and just mindlessly surround all of their atoms with a total of 8 electrons. Remember, the bond itself is 2, and then each of these, of course, is 2 itself. So you're going to be surrounding those with a total of 8. And then go through the math. So 6 plus 6 plus 6 is 18. Take that off the total remaining, which was 20. And now I only have 2 electrons to work with. And those last 2 electrons will just get thrown on to the central atom, in which we see it here. And that's pretty much it. There are some exceptions, of course, but as a general rule, that's kind of how we're going to go about doing this. So there's a little exceptions here. It's like, well, what if I run out of electrons? Well, in that case, we can make double bonds or maybe even triple bonds to fill these electrons. So in this problem here, I went through there and I surrounded the nitrogen with the 6 electrons, but it doesn't quite work because one carbon needs more and I don't have any electrons to take care of. Well, in that case, we can share electrons, showing that nitrogen is giving some of those unbonded pairs of electrons to carbon to fill carbon's octets. So now carbon is sharing 1 electrons from hydrogen. So it kind of actually, in this case, now has 2 from the hydrogen bond, and then 2 from each of the nitrogens. So it is kind of holding on to 8 electrons. And in this case, nitrogen is holding on to 8 electrons as well. So again, they're sharing them. Next one on here, which you probably did not do last year, is something called formal charges. And in doing this, we're trying to figure out what is the most stable format. So in this example here, we're looking at carbon dioxide. And you have 2 different ways we could put it together here, as you see at the bottom. You could put double bonds on each of the carbon-oxygen bonds there, and you probably already know that. But it also works out if you put a triple bond between one of the oxygens. So how do you decide which one works? Well, what we'll try to do is minimize the charges. So we look at what's called the formal charge, and we try to have as little charges as possible. So the one on the left here, in which we have 0, 0, and 0, is a more favorable arrangement than having a -1, +1. So we'll stick with the one on the left. And same scenario here, in which we have nitrogen, carbon, and oxygen. We have 3 scenarios this could be put together here. We could have the one on the left, in which we have a -2 + 1 arrangement, or we could have the one on the middle, which has a -1 over nitrogen, or a -1 over oxygen. The way we decide this one is, all right, I can't get past the charge. Somebody has to have a charge in this scenario. The element that is the most electronegative, and in this case it is oxygen. Oxygen will get the negative charge, so it's the most electronegative and it holds that. So that is the arrangement we look for when we can't get to zeros across. Is the one that is most electronegative gets the charge. Moving along, we have ozone, and this one gets a little bit tricky. is neither way I can't get this to work out where I have an equal bonding here. So this, we have that arrangement in which I could put the charge over there, or I could put the charge over on this side and get rid of it over here. Problem is when we look at the experimental data, we see that the bond length between these guys is the same. So that throws things off a little bit. It's like, well, how is this actually turning out? The reality, and let's see if I have room on the next slider. Yeah, I'll go over here. The reality is what we actually have is somewhere in between. So there's a couple ways that we could put this together. We have the electrons up here. Go ahead and put these here. And then what we can kind of do is either put a dashed line between these, or they may actually, as a difference, kind of do like a dashed line that kind of shows bridging between them to show that it is all kind of the same, but you have to depict that there is this floating double bond between these two on the bottom. And this is just another way to kind of show that with some density in there. And this is just another example of that exact same scenario in which you have that double bond that could float between these two. So it just kind of bounces back and forth between these two bonds. And similar situation in which you have, for example, a benzene ring. Notice these two arrangements right here. It's like, well, which one is it? Is the double bond, for example, on the bottom, or is it on the sides? Well, it's actually neither. It kind of, these bonds actually kind of are equally shared amongst the bonds. So we have this third drawing on the right, which better demonstrates what this thing actually looks like. All right, going back to how we make these bonds up, there are some exceptions to these. Sometimes the number of electrons don't always work out, so we'll take a look at these individually. So here's one in which we take a look at the total number of electrons, and nitrogen has 5, and oxygen has 6. So we have 11 electrons to work with, which is not easy to do because we like to pair them up. So we have one of these two drawings, either on the left or the right, that we can work with. And you can kind of pick. It's either one. And then you have this scenario here in which you have boron, which typically has, well, it's got 5 valence electrons. And neither one of these, again, is actually good, because what do we know about fluorine? It's very electronegative. So the one on the left has a positive, well, they all do. They all have a positive charge on fluorine, but boron has a -1. And we know that that's probably not going to be the case with boron having a negative and fluorine having a positive. So we have to do something differently, in which we'll see that's over here. So more likely what you're going to have is boron with not a full octet of electrons. It only has 6. Where the other scenarios in which we had boron with 8, those are not as favorable because it's more stable to have fluorine with a full octet and boron with only 6. So it doesn't have a full octet. Same scenario there. Some other weird examples is once you get down to the 3rd period on the periodic table, there's 2 elements in particular, but there are others, notably the halogens. But the ones we typically look at are going to be sulfur and phosphorus. Those 2 elements can have an expanded octet, so they may have more than 8. They typically, or can have up to 10 shared electrons. And you'll follow the exact same rules you did before as far as putting elements around there. But when you're trying to fit these things on there and you have that extra, in this case fluorine, you're not going to stick fluorine hanging off of another fluorine. It's typically going to be stuck to the central atom. This last little bullet, I left it in there just to show what the thinking was up until recently. The American Chemical Society recently changed their thought process and said that d orbitals really are not involved in the bonding. So you see how things change still all the time. How it happens, they're not really sure. All right, that's probably a pretty good place to start, or stop, I should say. We'll pick up with the lecture after this one.